Welcome, this is Mr. TG. This is part 2 of lesson 3-4 in Algebra 2A on linear programming. You should have at this time viewed the first lesson on linear programming. It shows you what it involves. It involves graphing a system of inequalities, finding a region of points that satisfy all the system, and then looking at the vertices of the region of points, which are the corners, and finding out which of those corners will generate a maximum or minimum value. This particular video will talk about one particular problem, and it's an application problem, so it will take some time and it involves some reading. So if we look in front of you, what I'd like to have you do at this time is read the word problem, read it thoroughly, read it a second time, and then when we come back, I'm going to hit pause right now. You come back, we'll talk about how to set this problem up using linear programming as our resource. So read through the problem. Okay, welcome back. So we're going to read through it together and talk about some of the important information that's highlighted in this problem. Wheels Inc. Makes mopeds and bicycles. Experience shows that they must produce at least 10 mopeds. The factory can produce at most 6 mopeds and 120 bicycles per month. If the profit on a moped is $134 and the profit on a bicycle is $20, and they can make at most 160 units combined, how many of each should Wheels Inc. make per month to maximize the profit? This basically is an application problem of linear programming. First, let's highlight some important information. Produce at least 10 mopeds, which means that they can produce 10 mopeds or more, 10, 11, 12 on up. And then it says here at most 60 mopeds, which tells us that we do have a limit in our factory. We can't produce more than 60 mopeds. And then another restriction here is that as far as bicycles, we can only make 120 bicycles per month at most. Now the objective here, of course, is to make as much money as possible. For mopeds, we're going to make $134. For bicycles, we'll make $20 each. And the other restriction that we have here, they can make at most 160 units combined. And that means, basically what that means is that we can make 160 bicycles and mopeds at the very most. So what we're going to do here is try to come up with what we call constraints with linear programming. This simply means that there are limits within this particular problem, and we need to find out what they are, and we're going to express those limits, and they're called constraints. We're going to express those constraints as inequalities. So let's start with this first constraint that we came up with, and I'm going to scroll this down a little bit. One of the constraints that we have is the number of mopeds. And as you can see, I've already set up the graph for you. You can look at the graph. I've made X represent the number of mopeds. I knew the maximum number was 160. I went up by 10, so there's an appropriate scale. My y-axis, I represent that as the number of bicycles. Again, maximum number of units is 160. Again, I went up by 10. So every line on this graph is a representation of a scale of 10. So since my mopeds are represented by X, let's start with that one first. We know that the number of mopeds has to be between 10 and 60. Right here it says at least 10 mopeds and at most 60. So the way we would write that as an inequality is you'd put the X, get this set up here, you would put the X in the middle. I'm going to change my marker here back to a pen, erase this. You would put the X in the middle, like so. And we want that X value to be less than or equal to, let's see, 60. And we're dealing with mopeds here, and the maximum is 60, and at most 10. So this is read as X, number of mopeds has to be between 10 and 60, or greater than or equal to 10 and less than or equal to 60. Then we talk about the restrictions that are placed on us for bicycles. That's, of course, our Y variable that we defined. So we're going to put Y here. And it says in the problem right here that 120 bicycles per month is the maximum capacity of our business. So we're going to say Y is less than or equal to 120. And it doesn't give us a limit on the other side. So we're going to, obviously, we can't produce a negative number of bicycles. So we're going to stop at 0. So anywhere between 0 and 120 bicycles can be produced. Yet another restriction that we have is the total number we can make, 160 units. Together, X plus Y has to be less than or equal to 160 units. We cannot manufacture more than 160 units. And yet one last restriction is, in this particular problem, negative numbers are not relevant. So what happens there is we simply say X has to be bigger than or equal to 0. And all that means in the context of this problem is that the number of mopeds produced has to be positive. It can be 0 or higher than that. And then, of course, the same is true with our number of bicycles. Y has to be greater than or equal to 0. When we place that restriction on the problem, we're essentially looking at just the first quadrant. I've essentially set that up for you. As you can see, we're just dealing with the first quadrant. Now, what I would like you to do, and I'll do this when I put this on pause, I would like you to graph all of these constraints or restrictions on the same graph. And remember, what we're looking for is the area of our graph that's going to satisfy all of these constraints. And then we'll talk about what to do with that once you're finished. So go ahead and graph those for me, and then we'll get back to you. Okay, welcome back. As you can see, I completed the constraints. I graphed all of them, and I'll kind of explain what I did here. The first constraint says that the number of mopeds has to be between 10 and 60. What you need to do for that is simply graph a vertical line at 60 and a vertical line at 10, and at 60. And we know from our constraints in the problem itself that it has to be between 10 and 60, the number of mopeds. So everything inside the region is going to work all the way to the top. Then we consider our constraints for bicycles between 0 and 120. So I drew a horizontal line at 0 because this is bicycles now, all the way up to 120. Everything has to be within that region. So far we're looking at a rectangular region here that works for both mopeds and bicycles. But yet we have another constraint, and that is the total cannot exceed 160. So what I did, it was a little bit simpler because we're scaling this graph, and I basically found the X and Y intercepts. And the X-intercept can be found by putting 0 in for Y, and the opposite is true for the Y-intercept. And I plotted points at 160 and just connected them. Now, the point of this, and then we need to test a point to see which region on the side of this slanted line is going to work. If you tested like a 0, 0, that would work. Everything below the line is going to work for our solutions. So what works for all three of these? Basically, as you can see, the yellow region is our feasible region for the number of mopeds and bicycles produced. For example, let's just pick a point right here. If I pick that point, I can certainly produce 20 mopeds and 30 bicycles. Now that would work for me. And it falls within our constraints. Or I could produce 50 mopeds and 20 bicycles. Or I can produce 20 mopeds and 110 bicycles. All these points, I could keep plotting them, will work. But what we're after here, if we're the owner of this business, is we want to be able to maximize our profits. That's our goal here, is to make it as much money as possible. So from that, we create what we call an objective function. An objective function is just the objective that we have in this particular problem. So in an objective function, we look at the problem and say, okay, our objective in this case is making as much profit as possible. Well, how much profit do we make on, let's say, a moped? Remember, X is the mopeds. How much is, well, we make $120. So we make $120 times X plus, and we make $20 for every bicycle that is produced. This is what we're going to consider as our objective function. It's the profit margin. So what you need to do now, and I'm going to put it on pause, is I want you to put every one of these vertices that I have here. This 60, 0 is a vertice of the feasible region, 60, 100, 40, 120, 10, 120, and 10, 0. I would like you to put them into your objective function for X and Y and simply tell me which of those will create the highest profit. And that will be the actual solution to our problem. So take time here and do that. Okay, welcome back. What I've done is I've taken all the vertices of the shaded region and I've put them in this location down here below. 10, 0, 10 mopeds, 0 bicycles, 60 mopeds, 0 bicycles. All these are corners or vertices. And we substitute them into this objective function. That's what I've done. You can just simply type it in your calculator. The results are as follows. If I produce 10 bicycles and no mopeds, we'll make $1,340. And then, of course, the objective is to make as much money as possible. So I finally have come to my conclusion of what I should produce in my company. 60 mopeds. So you should produce 60 mopeds and 100 bicycles. That is going to maximize your profit and allow you to stay within the constraints that are listed in the problem. So there's a lot of work here. I'm sorry for going a little bit long on this video, but there's a lot of things you need to consider when doing a linear programming word problem. So feel free, I think it'd be a good idea to run through this one more time to kind of see and understand what we went through. And I'm going to go through the word problems on the assignment with you in class. So hopefully you view this at home so you have as much time as possible to process this. Good luck with this lesson and let me know if you have any questions.